applications in different areas. So this area is actually on closer to medical statistics application. And this is on quadratic inference function analysis for correlated data. And I will talk about what quadratic inference function is, and also what generalized estimating equation and how they are related to each other, and how nonlinear shrinkage actually can help in this situation. So I'll give a very brief introduction to generalized estimating equation, the GEE, and also the quadratic inference function, the QIF. And why do we talk about covariance matrix regularization, and also how do we actually regularize large covariance matrix? So there's linear and also there's nonlinear shrinkage in the history of shrinking the covariance matrix. And in this particular data set where we use the quadratic inference function, we talk about how can we do actually nonlinear shrinkage in the QIF. And we also will later on provide simulation examples and a real data set on epileptic seizure data. And at the end of the talk, we will talk about some possible future research and a summary. So let's begin with the data that we are looking at actually. So mainly there are two main groups of data that we usually will apply the generalized estimating equation or the quadratic inference function. So one group of data is the data from longitudinal studies. So within longitudinal studies, so there are independent subjects observed over time. Okay, so these subjects they may have within correlation. So within each subject, so for instance, you may have a patient and you want to measure their blood pressure, measure their different symptoms over time. Okay, so you may have within each subject there are lots of observations which are some time points apart, and of course then within each subject those observations are correlated. Okay, so here I give an example. There's some patients with different treatments over time. So you can imagine that it can be applied to a lot of different situations, different patients, different measurements. And another situation actually is also longitudinal studies, but it's specialized. So it's called clustered randomized trials, or clustered randomized control trials. So subjects are actually clustered into independent subgroups. Okay, so different patients are clustered into different groups. Okay, so here instead of some medical examples, so here I give an example on non-medical aspects. So assessing the benefit of different teaching methods in different schools. So these students observed within the same school are actually correlated. Okay, so each school can be seen as a subject, and within each subject, all the students are actually observations, and we treat them as correlated individuals because they belong to the same school. Okay, for instance, if we want to look at some school-wise policies and how they affect different schools, then students within each school should be really treated as correlated individuals. Okay, so I don't mind all the equations, so I'll talk one by one with them. So let's begin by looking at what model we're using and what actually generalized estimating equation can help in analyzing those longitudinal data. So we actually assume that our observation yi contain actually different individuals. So you see yi1 up to yin. Okay, so if these are different schools, then there are n number of schools, and within each school there are ni number of students. Okay, so ni here can represent students and represent number of schools. ONI represent number of patients in a group, and N represent number of different groups that we are observing. Okay, and we assume that each group are independent of each other. Okay, and so we actually are doing some kind of generalized model. Okay, so we assume that the mean is equals to mu I, that is the expected value of each vector yi. At the same time, so we assume that there's a link function g that is known. Okay, and with this known link function, so g mu is x transpose beta. So it's basically a generalized linear model setup here. And we assume that this beta naught is d-dimensional vector. Okay, and this d can actually be growing with the sample size n. So later on we will see how this can be growing with the sample size n. And then another component is, so how do we estimate this beta? So our ultimate aim is, so we want to estimate this beta to try to see the effects of different covariance, this xij here. So in order to estimate this beta, so people come up with so-called a generalized estimating equation. So if you're not familiar, so this is the setup. So first of all, we try to find the derivative of this mu I beta. Okay, so this mu I beta is actually the mean function. Okay, so this mu I is here, expected value of yi. Okay, and through this known link function, so this potentially is a nonlinear function for beta, right? So we find this derivative, and another important component in generalized estimating equation is, so we need to specify a so-called working correlation matrix. All right. The situation is, so you have, for instance, you have different group of patients. Okay, so in many medical statistics examples, so you may have different group of patients, and within different groups, so you may have a different correlation for the data, for the observations within each patient. Okay, and so how do you know the correct covariance? So if you know all the correct covariance for different groups, then you can weight them appropriately in this estimating equation. But the fact is, in almost all situations, you don't know the true covariance within each subject, within each patient. Okay, so then how do we do it? So we specify some working correlation matrix. So we just hope that this specification is close enough to the truth. Okay, so that's generalized estimating equation. So this one big component here that we need to specify actually. So if we can specify this, let's say this is Vi, okay, the correlation within each group, okay, for the data, then we can actually weight it appropriately and then set up an equation like this. Okay, so it's the derivative with respect to beta times the precision of the correlation, okay, and then multiply with the error factor yi minus mu I. Okay, so in general, it's a nonlinear nonlinear equation in beta. Okay, and if we can solve this, then this beta, the beta that solve this will be the generalized estimated, estimating equation solution to this whole thing. Okay, then we take that as an estimator, and this estimator actually enjoys a lot of good properties. Actually, later on we will see when we introduce a nonlinear shrinkage. So the property involve asymptotic normality, and also if the correlation, even if the correlation matrix is misspecified, this beta is still consistent. Okay, still consistent to the true value beta naught. Okay, so this is one big advantage in the generalized estimating equation. All right. And well, so we need to specify a working correlation within each subject. So actually, this is still a disadvantage, even though we can actually consistently estimate the true beta norm. Okay, so there's later a paper come up to try to see if we can do better than that potentially. All right. So if you look back, so we need to specify ultimately a covariance, a correlation matrix Ri. Okay, so this Di is just working marginal variances. Okay, and this can be estimated from indeed within each factor itself. Okay, but how do we specify this working correlation? Well, in this paper, they try to come up with some form of basis for this working correlation. Okay, and this basis actually is the basis not for the correlation itself, but for the precision of the correlation. So the inverse of the correlation. Okay, so let's say you have different basis matrix. For instance, perhaps maybe a diagonal matrix, and then some structured matrix. For instance, in medical statistics, compound symmetry is very common. Compound symmetry means the diagonal is the variances, so you need to specify for different individuals, but other than the diagonal, all other elements are equal. Okay, so correlation among different subjects, you assume they are equal. That's compound symmetry. Okay, and this is a very common assumption on the many medical statistics examples. Okay, so independence, compound symmetry, or perhaps AR1 model. Okay, so because you're looking at time series, right? Remember, most of the time. So for those time points that are further apart, then correlation is actually decreasing as you looking at the time points further and further apart. So perhaps AR1 is not a bad idea. Okay, so this kind of structured matrix. So okay, we have an idea of this structured matrix should work. So why not form a sum of these and try to
just remind me.
Yes.
Clifford, if your correlation is decaying as you move away from the main diagonal,
yes.
What does the inverse look like? Is it tridiagonal? Is that right?
Yes. Yes.
So
if we are talking about AR exactly, then the inverse is
tridiagonal.
Exactly. Yeah. AR1 we're talking about. Yeah.
Yeah.
Yeah. So still, so it is basically like a decaying, or yes, for AR1 is just tridiagonal. So well, then the GEE, if you substitute this Ri inverse into this, okay, then the GE becomes this. All right. So it actually is a linear combination of these vectors GRI. Okay, so this GRI actually represents the vector correspond to the alpha basis matrix, and also correspond to the I group. Okay, so okay, this gamma Ri, okay, we don't know, but perhaps we don't actually need to know. So ultimately, remember, we are specifying this just to see, okay, so we need to specify this correlation matrix in order to efficiently estimate beta. So in doing so, can we actually specify another type of equation to estimate beta so that we can optimally weight those equations? Okay, so that's actually the idea. So this gamma Ri, in the end, doesn't matter. So how do we form another kind of equations to solve so that we can optimally weight them? So here is the details. So those GRI, we can actually form them into a vector, GI. Okay, so each GI corresponds to the I group, okay, for the data. And this quadratic inference function actually then proposed to minimize this. All right. So it involves the derivative of this g bar. This g bar is just the sum of the average of this gi factor, and then multiply with this R inverse. Okay, so this R inverse indeed will be the inverse of the expected value of the R. Okay, where the R is actually here. Okay, so it's just the covariance matrix of the GI. Okay, so assuming GI, of course, is it has expectation 0. Okay. So with this setup, you can see that if we can, there are number of equations again, and if we solve this equals to 0, then each equation actually will be weighted optimally, because indeed each equation will have the variance covariance matrix equals to this. And so we are indeed optimally weighting each equation. Okay, if we are solving the whole setup, the whole system like this. All right. So going from the GE, which you may not be optimally weighted, so these equations, to this QIF, a different set of equations, but you're optimally weighting those equations. Okay, so QIF is this idea. So even if you misspecify the system, okay, you misspecify the correlation structure VI, still you are optimally weighting these equations. Okay, it doesn't matter if you correctly specify or misspecify this. Right? But of course, remember, all these results are just asymptotic results. Okay, later on we'll see practically, of course, there's a price to pay in QIF, so we'll see later on. But here, even theoretically, there is one important thing that we need to remember. We are calculating this covariance matrix numerically. Right? So this is the estimated covariance matrix, basically, like a sample covariance matrix. Okay? So optimal weighting of the set of equations actually has an implicit assumption that this covariance matrix is going to be consistent estimator at least for the true covariance matrix. The true covariance matrix is the expected value of this, of course. Okay. So this is an important part. Okay, and in that paper, in the paper by Chu 2000 in the biometric paper, so of course they are treating the dimension D and M there as fixed. Okay, so D is the number of what is D here? So D is the so D is the dimension of the I think it's for the factor beta, and M here is the number of groups assumed here. Okay, so usually M can be assumed fixed, but the dimension of the beta, perhaps if you have more covariance, then you may not want to assume that it's fixed, especially in a lot of longitudinal data example, and may not be that large. Okay, so if you're using these asymptotic results, then perhaps you may as well assume that the is actually growing with the sample size n. Okay, so this is an important assumption. So is it true in practice? Okay, well, so here I specify those. So this basically needs to first of all, beta, an estimator in GEZ, it has to be close to beta. Okay, so you see in here, this covariance matrix is actually dependent on beta itself, which of course is not known to us. We need to estimate that. So usually in practice, we substitute the value of the beta by an estimator. So an estimator, perfect estimator will be a GE estimator. Okay. A GE estimator, remember, is consistent even if we misspecify the correlation structure. So we substitute that into here, and this is just an estimated correlation matrix for the true correlation matrix evaluated at the true beta node. So everything are estimated. Okay, so is it actually good enough? At the end of the day, as I said before, if n is not that large, then the dimension dm of the sample covariance matrix, so dimension is actually the product of the number of basis matrix and the dimension of the beta. Okay? So this dm actually can be large compared to the sample size. Okay, compared to the sample size. Then we may not have this result. Okay? We may not have this result at all. Then the whole optimally weighting these equations break down, basically. Okay? And you don't have actually an efficient estimator at all, even if using this QIF idea. So how do we solve this problem? So in this talk, we basically try to see if we can improve the result by actually shrinking this covariance matrix. Okay? And I was doing, my research is doing, nowadays is doing, part of it is doing nonlinear shrinkage of covariance matrix in different applications. So I propose to shrink this covariance matrix non-linearly in the eigenvalues so that this result may be closer to the truth. All right. But before that, okay, so what is nonlinear shrinkage and why do we need that? So here's a very, very simple example that I'm showing you as a motivation for nonlinear shrinkage. So this IIT data, and this data actually follows I think in simulations is a normal 0 and sigma square IP, but actually you only need them to be IID with mean 0 and variance covariance matrix for each YI is sigma square IP. Okay, so you are assuming a very nice structure for the IT, and let's suppose you are estimating the covariance matrix using the sample. So the sample is YY transpose divided by the sample size n. Now, expectation, of course, is unbiased, but it doesn't look good when especially P over N is approaching some constant, okay? So in particular, so that means what? That means the dimension of the covariance matrix is actually growing at the same rate as the sample size N. So if this is the case, then the eigenvalues, especially the extreme ones, are actually incorrect. Okay, the true eigenvalues are all sigma square.
Should be a maximum, right? Not a minimum.
Yes. Yeah, he's wrong again. Yeah, I haven't corrected it. Yeah. So is the maximum of this and 0. Okay, and the largest eigenvalue is going to sigma squared times 1 plus c squared, and then the minimum is going to the maximum of this and 0. So actually the eigenvalues, the extreme eigenvalues of the sample covariance matrix are a function of C. And this C, remember again, is the ratio between P and N. Okay? So you can see if P over N is very close to 0, then okay, largest and smaller still pretty much close to sigma squared. But as P and N goes to C, which is different from 0, then you can see lambda 1 and lambda n are going to be different from sigma square by some margin. Okay, and what is this margin? So I'll give an example. If P is 25 and n is 500, then the largest and smallest eigenvalues are actually 50% larger and 40% smaller respectively. Right? So even when P is 25 and n is 500, still the extreme eigenvalues will be hugely affected, hugely biased, basically. Okay. And so, in order to solve this problem, so Lidwell and Wolf in their annals paper proposed this. Okay, so basically, they try to propose an estimator, which is a function of the original eigenvectors of the sample covariance matrix. So this P here actually contains all eigenvectors of the sample covariance matrix. Okay, so we don't change them. But at the same time, if we are going to use this eigenmatrix, as the eigenvectors, then we want to find the eigenvalues that will solve this problem, okay? That will minimize the distance between this and the true covariance matrix segment in Frobenius norm, okay? Why do we use Frobenius norms? Because there's a very neat solution here. So the solution is the diagonal values rather than the true eigenvalues of sigma should be this. So it's a quadratic form in sigma, and is related to all the eigenvectors pi. So how do we estimate this di? Because obviously this di are a function of sigma, and this sigma is something that we don't know. Okay. So in order to estimate this di, so in the Annals paper, they actually propose some inversion formula, okay, using the technique in analyzing the Stiglitz integral. I'm not going to talk in details on how their formula works, but I'm going to talk about a data splitting method. Okay, so a data splitting method actually involves splitting the whole data into two independent sets. And within those independent sets, we calculate the corresponding sample covariance. All right. And so you have two different sample covariance matrices constructed from two independent sets. Okay. And usually, okay, the first set may be a bit larger than the second set. Right. So actually, you have to specify something like this. Okay. So let's look at the broad picture. So the broad picture is if we split it into two sets and construct two sample covariance matrix, then actually, if we use the eigenvectors from the first covariance matrix to form a quadratic form with the second set of data, so you see P1I is the eigenvectors from sigma 1 tilde, but the quadratic form is formed with sigma 2 tilde instead. Okay. Now, sigma 2 tilde is from y2, P1I is from y1, so they're independent of each other. Okay. So we want to form a quadratic form such that these eigenvectors are independent of the matrix in the tree. Okay. And if we do so, then under certain conditions, okay, which are not difficult to satisfy, then you actually will have a quadratic form like this. So this P1I transpose sigma 2 tilde actually will be close to as if sigma 2 tilde is correctly estimated as sigma, the true covariance matrix. Okay. So while the sample covariance is is unbiased, but the eigenvalues are difficult to estimate as the true value. Okay. This quadratic form actually is asymptotically correctly estimated, where sigma 2 tilde can be replaced by sigma asymptotically. All right. So this is the idea, and we use this idea to form a covariance matrix like this. And we say that this is a nonlinear shrinkage estimator for the covariance matrix. Okay, so you see all the diagonal values are actually a quadratic form between P1 and sigma 2 tilde. All right, and the essential thing is these two are independent of each other. All right, and okay, let's skip this efficiency thing. So let's not look at that. Let's go back quickly to what we were talking about. We were talking about the quadratic inference function. Okay, in that setting, we have a covariance matrix that we want to estimate, which is a function of the beta itself. Okay, so how can we apply this data splitting idea in the QIF setting? Well, we want to solve. Okay, we use a similar setup, so we want to solve a problem like this, where this P actually is from the sample covariance matrix. Okay. And remember, this Rn beta is actually the sum of GI transpose and then divided by n. So those GI factor are actually evaluated at the true value beta naught. Okay. So here, assuming beta naught is known, then we can actually find an eigen decomposition, and this P is the eigenvectors of this eigen decomposition. All right. And if we solve this problem, then we can easily find what minimize with respect to D. Okay, so this D will be all the diagonal values of this quadratic form here. All right. And this matrix, of course, is unknown to us. First of all, beta naught is not known to us. Secondly, this expected value of Rn, of course, again, is unknown to us. So using a very similar setup as before, so we replace this expectation by some estimator, okay, using the data splitting idea. But this time the data splitting is a little bit more intricate than before. So before we just split the data into two independent parts. So this time we split it into different groups, okay, different groups. So you have n patients, you're observing n patients. Well, perhaps you can split them into L different groups. So L can be 2, L can be 3, doesn't matter, okay. So split them into different independent groups where each group maybe are very small, okay, 1 or 2 or 3 patients. Then you can calculate these two different quantities. The main idea is these two different quantities will then be independent of each other. We are assuming the observations, remember, are independent vectors. Okay. The correlation actually is within each patient. Okay. So then this one without the Drake group is then estimated for the covariance. Now, and the covariance, of course, can be estimated using the Drake group alone. Okay. Then, so you can form these two covariance matrices. And for the first one, you can you do an eigen decomposition like before. All right. And then, so you can substitute all these values. Now, this P can be substituted by this P1J beta. And this beta can be estimated by some consistent estimator like the GEE estimator. All right. So we write this as P1 bracket J. Okay, so it will be evaluated at this beta tilde, consistent estimator for beta. At the same time, the true covariance matrix, so here expectation of Rn is replaced by R bracket J, R sub bracket J. So which is evaluated at a small group, and beta is replaced by beta tilde. Okay. And then we sum. Of course, we need to sum over from 1 to L. Okay. Then this will be our estimator for the covariance matrix Rj. Okay. All right. So how will this estimator be doing compared to just the usual quadratic inference function, where you just using sample covariance as the covariance matrix estimator? Okay. So we will see in a minute. Okay. So so here I provide some results. Okay. So these may not be extremely important, but maybe let's go over it very quickly. So we assume that the eigenvalues of this Rn beta tilde are distinct, and also these are a little bit restrictive, so I hope to relax it. Over this half a year, I'm doing some intense revision on other papers, so I don't have time to develop it further, but hopefully, so this summer I have time to develop more in this theory. So here, this dm times the maximum group size has to be slower than root n. Okay, so it is a little bit restrictive, but in many small data examples in longitudinal data set, this actually is okay. But maybe perhaps we can modify this to accommodate more larger longitudinal study later on, hopefully. Okay, so we have these results. All right. So this result basically is to assure you that we are substituting this P1J. So will this P1J is going anywhere? Okay, so this will be going to at least the usual eigenvectors for the sample covariance. Okay, and at the same time, this sigma m actually is maybe close to this sigma ideal. This sigma ideal is given by this, where you have P here and the true covariance matrix in between. Right? Okay, so if we have, because you have independent data, so you actually can permutate the data and actually evaluate this sigma m again. Right? We are splitting one to n into different groups. If we permutate this different data and do this over again, we can obtain different estimator. Okay? And so we can try to average this permutated estimator. And finally, obtain a final estimator for the covariance matrix. And this covariance matrix is, remember, is to try to optimally weight those equations in our quadratic inference function. Okay. So here are some theoretical aspects. So this iterative algorithm is actually the same as the QIF. In QIF, so you just replace this by the usual sample covariance, the Rn inverse. Here in my algorithm, so I just replace this by my nonlinear shrinkage estimator. Okay, so otherwise everything is the same. And ultimately, so even if we replace this by our nonlinear shrinkage estimator, then we can prove that we have this asymptotic normality. Okay? So this asymptotic normality, okay, so very complicated estimator for the covariance matrix, but you can see the covariance matrix now is rather than just the inverse of R, so you can see is the sandwich formula of the precision matrix of our nonlinear shrinkage estimator and the true covariance expected value of Rn. Okay, and well, is it efficient enough in the end? So that's the big problem, right? We want this to be practically more efficient after substituting our nonlinear shrinkage covariance estimator. Right? So we'll see. Okay, so we'll see by a simulation study. And so let's look at very quickly the simulation setup. So we first of all use Gaussian data, so very standard Gaussian data, and length of each group yi will be random between 3 and 6. So you assume that within each patient you obtained 3 to 6 observations. Okay, and the true correlation structure is compound symmetry. Okay, so diagonal value will be 1, and then non-diagonal will be 0.8. Okay, so very highly correlated observations basically. And we also look at top list matrix. Okay, so one example is compound symmetry, one example is top list. Top list basically is the off-diagonal values are the same values. Okay, so from 0.8 to 0.1. And so we just set up our data like this, y equals to x beta naught plus this covariance matrix, so 1.5 times the correlation. And the covariance will be something like this. Okay. All right, so with this setup, can we, first of all, how does the GEE compare to the QIF, and how does QIF compare to our nonlinear shrinkage estimator method? So we will see it here. So let me explain very quickly. So remember, the true correlation structure is compound symmetry. Okay, that's our simulated data, and here we use n equals to 30 in this table. Okay, so 30 patients, and this NSQIF is the name of our method, nonlinear shrinkage in the QIF. So remember in QIF, we set a basis matrix, right? If we increase the number of basis matrix, you increase the number of equations, basically. Okay. So it's a compound symmetry, the true correlation. Now here we include not only compound symmetry basis matrix, but also an independent matrix. Independent means just a diagonal matrix. Okay. So you're basically adding two sets of equation. One set corresponds to independent structure, another set corresponds to compound symmetry structure. Two sets of equations. Remember, dimension is d times m, so here m equals 2. Okay. And here's the result. So we calculate basically just very simple L2 error, average of L2 error, okay, of the beta norm. So here we can see if GEE is using the correct correlation structure, of course, it will be the best. Okay. And QIF here, we are using correct structure, but we are adding another set of unneeded structure. Okay. So in QIF, okay, we claim that we are optimally weighting all the equations, even if we misspecify the correlation structure. Here we are misspecifying. We are including a true structure, but there's no independence needed, but we add it anyway. So we are misspecifying still. And the performance is actually not as good as GE. So if we add more unwanted equations, in practice, still, you will suffer, okay? Despite the asymptotics, what the asymptotics tells you. And look at the typical QIF, okay? So that's the main thing we want to compare. So this QIF still using the same independence and compound symmetry structure, so you can see the error is larger than our proposed estimator, okay, or average. And there actually exists some nonlinear shrinkage QIF, okay. So that's where the nonlinear shrinkage come from. Actually, I see that. So the most recent advancement is using nonlinear shrinkage on the estimator of the covariance. Okay, so I think I can derive a nonlinear shrinkage. So of course, nonlinear shrinkage will be better than linear shrinkage. And here, so we compare different type of situations. So here, we exactly specify correctly the true correlation structure. So we use compound symmetry. Okay, so when QIF is using only compound symmetry and GEE, then they basically are identical. Right? And at the same time, there's some different type of structure. So here, the true correlation matrix is a Topley structure. If we use a Topley structure, so how about we're using AR1 or compound symmetry, so it's a little bit misspecified, but very close enough. Okay, so you can see that our estimator is even better than GEE. Here n is 60. If n is 30, then I think GEE may still be better. Okay, GE after all is simpler in its structure. The simpler, the better, basically at the end of the day. Okay, but n is 60, then okay. So this QIF is still better than GE, even if we have two sets of equations correspond to two different correlation structure. And well, this QIF, you see, I always include the independent set of equations because their outcome actually have that independence as a basis. Okay, so I cannot remove that. I actually want to remove that to compare them. Okay, anyway. So yeah, so it's actually not a good idea to put independence as a structure always. It's not a good idea actually, but that's the outcome you can get from many practice. All right. So again, you can see, well, linear shrinkage just a little bit better, but in using our nonlinear shrinkage, so if we try to use different correlation structure, then we can potentially be much better off. All right. And we have another set of simulation, and this set of simulation is for Poisson data. So we haven't specified the type of data actually at the we actually can apply our method to count data as well. Right. So for this Poisson data, well, link function is of course log link. Okay, and so here we use log link indeed, and the intercept, I mean the covariates are generated similarly as before, and we are using different correlation structure again. Okay, and the simulation is result is in here. Okay. So this time we use n is 60, because when n is smaller, then things are quite difficult for Poisson, for count data, I think. So I use n is 60, okay, so everything stabilized a bit. And you can see again, so true structure is topless, so decaying values. And here I use independence and compound symmetry. Okay, so all of them are misspecifying the correlation structure anyway. All right, and you can see this will be worse than this. Okay, so GE using just compound symmetry actually is better than even nonlinear shrinkage using compound symmetry, but also include an independence set of equation. Okay. And at the same time, if we use another set of correlation structure which are closer to topless, so AR1 here, then potentially we can be better than GE, especially GE here still misspecified the topless. Compound symmetry is not decaying. Okay, so topless is decaying. So here I actually include n equals to 30. You can see the error is much bigger actually. So still the true structure is still topless, I think. And if we use AR1, so AR1 is the closest that we can approximate the topless structure, then the nonlinear shrinkage and GE, they are very similar. Still, GE will have an advantage. It's also simpler, okay, GE. At the same time, the typical QIF and the linear shrinkage, well, they have to include independence, but so the error is bigger. Okay. And so here basically is the simulation results. So let's look at it very quickly, finally, real data analysis. So this data is actually some epileptic seizure counts data of a very small group of patients, 59 patients. Okay? And each patient is observed for 4 successive 2-week intervals. So for each 2-week interval, there's some observations made for each patient. Okay? And there's different covariates. So the main objective is X1. They want to see if they receive drug correctly. They receive drug and get better, basically. Okay. So this one particular drug, and of course another group is the standard procedure. You give them some placebo. Okay. So receive drug and not receive drug. At the same time, we control for other very potentially very helpful covariates to try to see if the drug is actually marginally helpful. So this actually, you can imagine, will be a very important covariate. So this actually the seizure counts in an 8-week prior period. So you can imagine if you have a lot of seizures prior to the experiment, then you're going to have expected to have more during the experiment. Okay, so this is very important covariate, and we also include age and the time interval in the observation. Okay, so therefore a covariate, and we want to see which covariance is important, and in particular is X1 important. So let's look at this data. Ultimately, the data set we can find 4 very distinct outliers. So without the outliers, we can see that, okay, so beta 1 here corresponds to X1, and the is very, very close to 0. Okay, we look at the standard errors and errors 0.01. Not good, okay? And we move in these 4 subjects, so from 59 down to 55, then everything changed quite drastically. So 4 outliers removed here. But still, x1 is getting much larger, still is not significant compared to the standard error. Okay, so here we're using independence and compound symmetry for our QIF, and for GE you're just using compound symmetry. But no matter what we use, results are quite similar actually. No matter what basis matrix we use, and no matter what different GE, typical QIF, they are very similar. Okay, so the results is quite conclusive that the drop is not really that effective. Okay, so that's the conclusion. Of course, the prior seizure counts, beta 2, is very significant. That's expected. Okay, so that basically conclude the talk. So let me give you some take-home message. That's the important bit. So when dimension is larger, sample covariance matrix is not a good estimator, so eigenvalues are heavily biased. And this situation is actually bad for the QIF analysis. And so we propose nonlinear shrinkage of the covariance in the QIF, okay? And to try to see if we can outperform the typical QIF and also the linear shrinkage QIF. And at the end of the day, we find that, of course, from the practical example, so our QIF is better than the linear shrinkage and also the typical QIF. Okay? And from the simulation, if we look closer, so the more important part is still good choice of working correlation structures. So in QIF, if you include more structures, you include more number of equations in your system, which is actually not good, okay, in practice. So still, we want to find as small number of working correlation as possible, and those working correlation are as close to the true correlation structure as possible. Okay. So this is still some problem that we want to solve one day. And there's some direction, so can we combine this with penalized estimation to penalize actually useless equations? So in previous examples, so we include independence, compound symmetry, AR1. So can we include all of them and then have some screening procedure to screen out those useless equations first? Okay. So this may be one direction that we can do. Or another completely different direction, actually related, is an empirical likelihood approach. Empirical likelihood actually has a component of penalized estimation. So this is what I hope to look more into, and hopefully can develop some more procedure, more automatic. Okay. So that basically is the end of my talk. So thank you for listening. Thank you. This J is small.
Yeah. You have this split data into 2 parts, and you ask the second data part.
Actually, very good question. So I think this size of SJ can does need to be of a decent size, and this size has to need to satisfy something like this. Something similar to here. So this you can imagine is the size of the SJ. And n is the total number. Okay, so the group size, those small group size SJ should actually have a decent number of elements, which can be assumed to be growing with n as well, but can be much smaller. You can see, we just need to satisfy this kind of thing here. I think I may have a specification. And I think ultimately we only need this. Okay. But you're right, so the SJ I haven't specified. All right, so SJ must have order root n. Okay. So n is, so here, so this total number is n, right? So we want to group them into root n, basically. Okay, so L here may be going to infinity as well at a rate root n.
Yeah.
And then we group different patients into, each group may have size root n, something like that.
But in the intuition, you think about like SJ, if you have more data, that's better, right?
Yeah, that's the intuition, correct. But in here, let's look back at this. In here, so this sigma 2 tilde have size m, right? Y2 have size m, actually. And at the end of the day, m doesn't need to be that large. Again, this m is of size root n.
Okay.
So, yeah, of size root n is enough. Actually, can be even smaller, but I think root n practically is the best. Okay, but it theoretically can be even smaller. Okay, as long as it's growing to infinity a certain way. I can't remember exactly the smallest rate, but I use root n because in practical examples it's better. And the main thing is actually these p. Okay, so if you include more data for estimating these eigenvectors, then the practical performance is better.
So on this page, you have this indicator function. Oh, and that
Oh, yes, this is
one
indicator
is
function,
only
yes.
for the eigenvalue of sigma tilde 1. And here, so you prove this result for any fixed x?
No, this lambda 1i is actually for this sigma 1 tilde.
Right.
So is the I largest eigenvalue for sigma 1 tilde. Yeah.
So you prove this for each fixed x in the.
Yeah.
Okay. It's a simple question.
Yeah. So yeah, so hopefully I can develop the theory further. It's just not enough here. I think. It's unfortunate I don't have time before to try to develop more fully. So hopefully this summer I can use more time to think about how to improve the whole QIF thing here. So thank you for listening. If
Thank
you
you
have
very much.